Second experiment regarding the dilation of time is known as the muon experiment. All right, so these are elemental particles. They have a lifetime, so which means that they live about 2.2 microseconds while at rest. So it's measured. They come into existence within a flash. They're done. They turn into energy. All right, so these particles are created in the upper portion of the atmosphere, and they are usually traveling very near the light speed, which is 99.8% of the light speed coming in. Yeah. Within the span of their lifetimes, okay, because they last only 2.2 microseconds at that speed, they should only travel about 600 meters. But here's the problem. Instead of traveling 600 meters, they actually travel all the way down quite a bit. Okay, they travel about 4,800 meters, which means that because they're moving very near the light speed, within their own reference frames, they exist only 2.2 microseconds, and relative to us, they happen to live a lot longer. Actually, they exist 60 microseconds. So their times, their lifespans become dilated, which means that their times slow down relative to us. That's what it means. All right, so I thought I had a video, but let's move forward.
Is this like the Dune experiment?
It's like what?
The Dune experiment done at Fermilab?
Oh, yeah, it's the same idea. Yeah, these particles at Fermilab, I mean, in their rest reference frame, if you place them in, if they're not moving, they don't live that long. Okay, so they just vanish. But when they start to approach the light speed, their times become dilated, which means that their times start to slow down. All right, so what do we have? So we got the muons at rest. They exist only this long, and then when they start to move at 99.8% of the speed of light. So what happens to their times, and how far do they travel? All right, so this is their proper time. So within their own reference frame, they will exist only a microsecond to 2.2 microseconds. While they're moving at 99.8% of the speed of light, what happens to their time? All right, so their time is going to become dilated, which means that their time is going to slow down. So relative to us, their time is going to become expanded. That's what it means. When you plug the numbers in, all of a sudden we end up getting a much longer duration for their lifespans. All right, so how far would they travel? Without the time dilation, just using their own speed, okay, and they will only live a fraction of a second. You will get something roughly about 600 meters. Okay, so I made a mistake. This should be the non-relativistic. This should be the time within their own reference frame. So within own reference frames, as far as they're concerned, they're moving about 4/10 of a mile. In our reference frame, all right, I changed the notation there. In our reference frame, because their times will slow down, they will move roughly about 6 miles. All right, so in our reference frame, their time becomes elongated, which means that their time slows down. So they get to move about 6 miles. Okay, there was supposed to be a video regarding this. All right, so that's the actual experiment. Hopefully it's going to work. All right.
Even when the theory is as beautiful as Einstein's, it needs testing. And there is a test of relativity in a phenomenon called the decay of cosmic ray mu mesons. A quarter of a century ago, Dr. David Frisch of MIT and Dr. James Smith of the University of Illinois filmed a classic experiment proving the reality of the relativistic time dilation. They did it by measuring the flux through the atmosphere of a radioactive subatomic particle called the mu meson. Created at the top of the Earth's atmosphere by cosmic rays from outer space, mu meson zooms straight downward at nearly the speed of light. But laboratory experiments, such as the one done here by Smith, show that mu mesons disintegrate naturally after an average life of only 2 millionths of a second. That means that even going at near the speed of light, they shouldn't make it very far through the atmosphere before decaying. Or to put it differently, when Frisch and Smith observed 568 mu mesons in their detector at the top of Mount Washington, they calculate that only 27 per hour ought to make it to the base of the mountain. But when they cart their equipment down to sea level, they find almost as many mu mesons as they had at the top, 412 per hour. Of course, Frisch and Smith really aren't a bit surprised. The reason for the discrepancy is spelled out by the theory of relativity. Traveling at nearly the speed of light, the mu meson's internal clock runs slow so that, as viewed from Earth, they take much longer on the average than 2 millionths of a second to disintegrate. Or, to put it differently, as viewed from the frame of reference of the mu meson, the Earth's atmosphere rushing upward at nearly the speed of light. Its Lorentz contracted to such a degree that the particle can easily make it all the way to the ground in only 2/millionths of a second.
All right, so with respect to mu mesons, the space is going to contract into directional motion. And from our perspective, mu mesons time becomes diameter. All right, so once again, the same summary. Light travels at the light speed regardless of the motion. Time is going to slow down and near the light speed with respect to a non-moving reference frame, like the Earth reference frame. Space is going to contract only outside of your reference frame near the light speed. Speaking of the contraction of space, all right, so mathematically, how does this look like? Let's focus on that one. All right, so there are two things that we're going to be looking at. So we got this astronaut. There's a meter stick, so it's going to have a length, which is going to be a meter. This spacecraft is cylindrical. It's going to have a length and a diameter. The length of it is going to be 82 meters. The diameter is going to be 21. And it's moving at 95% of the light speed. All right, so the question is, what happens to the diameter and what happens to the length of the spacecraft? Okay, so what happens to the diameter and what happens to the length of the spacecraft? All right, it's a contraction of a meter stick. It's not a meter stick, it's just the spacecraft. So title is not the right title. All right, so diameter is going to be 21 meters. The length of it is going to be 82 meters. It's moving at 95% of the light speed. All right, so it's more of a first part is a conceptual exercise. What happens to the diameter? Nothing is going to happen to the diameter because contraction only occurs along the direction of motion. All right, so the diameter is going to remain the same. So it's going to be 21 meters. All right, but the length of the spacecraft is going to contract relative to a stationary observer outside. And then this is the relative by the relativistic factor. So original length is going to be 82 meters. And from the perspective of someone who's stationary relative to the spacecraft, it's going to look shrunken. Its length is going to look like 25.6 meters. All right, so that sort of stuff is kind of tough to measure.
As the light leaves the star and the star wobbles, the spectrum of light from blue through red shifts back and forth in space, and that Doppler shift of the light back and forth tells us that in fact there's a planet yanking on the star.
As the star wobbles towards the telescope, its light goes blue. As it wobbles away,
We know something about the contraction of space because of the relativistic Doppler shift.
red.
And that amount of Doppler shift
Something that we discussed yesterday regarding
allows us to determine
whether or not the stars are planets.
the mass of the planet and the orbit of the
If a galaxy is moving away, its light is stretched. The interval between wave crests gets longer.
All right, so that's going to be your redshift.
The light appears redder. The faster it's moving, the redder the light. If a galaxy
As the space is expanding.
is moving closer, the light is compressed and appears bluer.
So it's going to be blue shifted. So that's the contraction of space in the direction of motion, or the expansion of it.
In addition to revealing a star's composition and temperature, stellar spectra offer clues about the motion of stars.
In the last century, it was discovered that the wavelength of light could be changed or would be changed if the object emitting the light was moving toward the observer or away from the observer. And this has become known as the Doppler effect for one of the earlier studiers of this effect. We can also hear it in sound. The pitch of sound depends on whether something is approaching us or receding from us. The Doppler effect also applies to stars and starlight.
All right. All right, so whenever you're ready.
B.
All right, so Lucas, I'm going to give you 2 points for B. Is not correct. All right, so relative to a stationary observer, the moving object is going to look
Shorter.
shorter, right? Yeah, because it's going to look contracted in the direction of motion. So the best answer is going to be C. So for the previous one, those of you guys who pick C, give yourselves 2 points. Okay, remember, stationary observer is the person who's outside. Looking at.
Okay.
Yeah, I mean, when this object starts to reach a speed near the light speed, its length is going to approach to 0. So A is the best answer. Give yourself 5 points. Those are guys like A, give yourselves 2. B. All right,
Does not
B
change.
does not change. So only in the direction of motion the contraction occurs. Width is 90 degrees of motion, so nothing is going to happen only in that direction. So those of you guys who pick B, 2 points. Those of you guys who say B, 5. All right, so what if we could travel at the light speed? Okay, so all of a sudden, what do we have? We got the contraction of space, dilation of time, and notice that there's nothing about masses yet. Okay, so here's the problem. Einstein is thinking, what about the light speed? What would prevent you from reaching the light speed? Number one, you know the space is going to contract to a point when you approach the light speed. All right, so in the direction of motion, space is going to contract literally to a point. So boom, boom, boom. B becomes C. If that's the case, everything is going to contract to a point. That's it. All right, so if you're moving at the light speed from here to New York City, you won't be able to perceive space, which means that's a magic trick. All right, Chicago is going to turn into New York City. If you're a particle of light traveling across the universe, this universe simply does not exist, guys. All right, if you're moving across this universe from one end to the other end, you will not be able to perceive this universe. In the direction of motion, the universe is simply going to shrink to a point. You cannot perceive anything of this universe. So space is going to contract to a point in the direction of motion. So that's one conclusion. And the second conclusion is, okay, so we're done with the time, moving forward, come on. Okay, so what happens to the time? So how long does it take for you to go from here to a galaxy which is 100 million light years away at the light speed, or all the way across the universe for that matter? All right, so at the light speed, oh my God, you end up getting T. In your reference frame, 1 single second is going to be eternally long. This is what it means. Put differently, it would take no time at all for you to go across the universe. All right, so if you're moving at the light speed, you would not be able to perceive the universe because the universe is going to shrink to a point. Also, from your reference frame, it would take no time at all for you to go through the universe, across the universe. So the question is, why is the light speed
What Einstein
constant? What will prevent you from actually approaching the light
did
speed?
was completely turn the problem on its head.